Hey guys, Jake here coming at you with another math lesson today. Happy Tuesday, doing it live a day later than normal this week, doing it on Tuesday. Wasn't able to go live yesterday, but glad we're able to make it up today. And today we're going to be going over some integration by parts problems, some integration by parts examples. Going to also touch on just kind of how I actually, decide when I'm doing an integration by parts problem, how to pick the U and how to pick the dV. So just kind of what my thought process is on that, so that you can do integration by parts problems a lot easier on your own. If that sounds good, be sure to stick around to the end of the video. And I do have at the very end kind of a fun problem, a bit of a challenge problem that I think will be helpful for you to see. So without further ado, let's go ahead and jump into the examples that I have prepared here. So before I do, just a couple of quick things. The integration by parts formula is one of the formulas that's on my Calculus 2 cheat sheet, or my integral calculus study guide. If you want to check that out, there is a link down in the description below, or in the pinned comment, where you can get yourself a copy of that. It's available for instant download, so should be a huge help for you as we go through these different Calc 2 problems. But also, if you have any questions along the way, please feel free to drop those in the live chat. I always want to try and answer whatever questions for people I can. I'll try and check questions along the way, but I'll definitely be checking them in between each problem. Even if they're not related to the problem that I'm talking about, go ahead and drop whatever questions you have, and I'll see what I can do to help answer whatever questions you have. But let's go ahead and start with this problem here. So we're going to evaluate this integral using integration by parts with the indicated choices of u and dv. So in the example, the textbook where this example came from, it does actually give this integral that we're going to be solving. So the theta times cosine theta d theta. And then it actually tells us right next to there, and I know I didn't write it here yet, but it actually tells us in this case, we're going to use u equals theta and dv equals cosine theta. And technically you do actually want the d theta on there as well. So just in general, kind of a quick note about these integration by parts problems. Really what you're going to be doing as you do these types of problems is applying the integration by parts formula, first of all. So we'll get to that formula in just a second. But the first step in using that formula is determining which piece of your function is going to be your u and which piece is going to be your dv. Well, in this case, it's been given to us, so that obviously makes things a lot easier. But in general, when I'm trying to think about how to choose your u versus your dv, a good rule of thumb is you want to pick your u to be whichever thing is going to be easier to take the derivative of, and your dv to be whichever thing is going to be easier to take the integral of. So this is a good example of that, because in this case, they told us to do u equals theta. Well, if we think about the derivative versus the antiderivative of theta, and keep in mind, since we do have a d theta here, that's telling us that theta is our variable. So therefore, the derivative of theta with respect to theta is just 1. Well, that's much easier than the antiderivative of theta, which would be 1/2 theta squared. So 1/2 theta squared would be the antiderivative, and then 1 is the derivative. So 1, really either of those wasn't necessarily easier or harder to find, the derivative versus the antiderivative, but the derivative of theta is much simpler. It's going to be easier to work with on the next step. So another thing to kind of point out as well, in this case, the other function that we're trying to decide is cosine of theta. Well, usually if you have a trig function like cosine or sine, it's not really going to be easier or harder to take the derivative versus the antiderivative, right? The derivative versus the antiderivative of sine is just positive or negative cosine, and vice versa as well. The derivative or the antiderivative of cosine is just positive or negative sine. So it's not really going to make a difference. So in this case, since theta being the thing that we want to take the derivative of, and the other term not really making a difference, that's what we want to go with. So the next step in applying these integration by parts problems is to apply the formula. So let's start with that formula. Like I said, this formula is actually one of the formulas on my integral calculus cheat sheet. There's a link down in the description or the pinned comment where you can get yourself a copy of that. But the formula just says that if we're taking the integral of u times dv, that integral is going to be u times v minus the integral of v times du. So, you know, in this case, we've already been given what our u and our dv are. Normally, when you're doing an integration by parts problem, that's going to be the first thing that you want to figure out. That's going to be kind of the first step. In this case, since we already have that, the next step is going to be to figure out the du and the v, which to do that, all you have to do to find the du is just take the derivative of u. So like I already said, the derivative of theta with respect to theta. We know it's with respect to theta because we were given d theta at the end of our integral. This d theta is really just an indicator of what our variable is in this problem. So in this case, d theta tells us it's theta. The derivative of theta is just 1. It's not like implicit differentiation where you have to, you know, think about what variable you're taking the derivative with respect to or anything like that. It's, you know, in this case, we only have thetas. The d theta tells us that's our variable, so that's convenient. So then we have to, and then also here, actually, you want to put a d theta on here. So basically, you're going to put a d theta along with your du and your dv term. Again, they're just kind of indicators to tell you what your variable is in that specific little piece, basically. If this said dx, we would put a dx here and a dx here. Since it's d theta, we're going to go d theta, d theta. So then to find our v, what we need to do is take the antiderivative of our dv. And in this case, when we take the antiderivative of this, the d theta tells us that we're integrating with respect to theta. The d theta is going to fall off when we take the integral and get our v term. So the antiderivative of cosine is going to be negative sine, I believe. Nope. Positive sine. Yeah. So the antiderivative of cosine theta is sine theta. Because the derivative of sine theta is positive cosine theta. Okay, so now once you've figured out your u, your v, your du, your dv, once you have these 4 pieces, the next step is just to plug these 4 things into this formula. So basically what we were given, what we started with, was our u. So this was our u, and then this was our dv. So now what we're doing is we're converting the integral of u times dv, which we have here and here, into u times v minus the integral of v times du. So now we just use this kind of conversion with these 4 pieces here to figure out, you know, essentially what this is going to give us is another integral, a different integral, which should be easier to actually find. So u times v is going to be theta times sine theta minus the integral of v times du. So minus the integral of 1 d theta times sine theta, which is just the same as sine theta d theta. So now notice, even though we still have an integral here that we have to find, what we just did was we converted having to find the integral of theta times cosine theta into just having to find the integral of sine theta, right? We don't have to actually integrate this stuff out here anymore. So these pieces have been kind of removed from the integration process. They've been accounted for, basically. So now to actually figure out what this is equal to, this this theta times sine theta is just going to remain out here, and then we just have to integrate sine theta. Well, the integral of sine theta is negative cosine theta. And then keep in mind, we did still have this minus sign out here. So now this minus sign is going to cancel with that minus sign. And we're just going to get theta sine theta plus cosine theta. Perfect. So now we know that theta sine theta plus cosine theta is the antiderivative of theta times cosine theta by using the integration by parts formula. Alrighty, so let's see. I'm not seeing any questions here in the live chat, so we'll go ahead and continue on to the next problem here. So next we are going to evaluate the integral, which is the integral of x squared times cosine of mx dx. So in this case, m is we're going to treat as an unknown constant. So this is not a variable, it's just a constant. Basically, this would be the same as saying like the integral of x squared times cosine of 4x or pi x or whatever. M is just going to be some unknown constant. So again, same kind of process like we did in the last example. The first thing we need to do, first step of any integration by parts problem, is to first just figure out what do you want to make u and what do you want to make dv. So this is really not too different from the last example we did. Because again, if you have sine or cosine, usually it doesn't really matter whether you take the derivative or the antiderivative. The derivative of sine and cosine or the antiderivative of sine and cosine, they only differ from each other by a constant. So if we're taking the derivative of this term or the antiderivative, it's not really going to be any less or more complicated. It's just going to differ by a constant, which when you're integrating, you can just pull the constant out of the integral, which means it's really going to make no difference in the integration process. However, looking at this term here, x squared, let's think very quickly, what's the derivative of x squared? Well, the derivative of x squared is just 1 if we're taking the derivative with respect to x, which we know because we have a dx at the end of our integral. And then if we're taking the antiderivative of x, we would find that just using the power rule. I'm sorry, the derivative of x squared is not 1. I did that too fast. The derivative of x squared using the power rule is going to be 2x. Okay. Then the antiderivative of x squared using the power rule is going to be 1/3 x cubed. We would raise our power, whereas here we're lowering our power. So usually if you have a power function or a polynomial as one of your possible options for u versus dv, typically, and I'm not going to say always because depending on what your other term is, you might want to do something differently. But typically, taking the derivative of a power function like this, where you have your variable raised up to a constant function, whether you take the derivative or the antiderivative, you're just going to do that using the power rule, right? Which means you're either going to lower the power by 1 or raise the power by 1. Typically, it's going to be better to lower the power by 1 because each time you do this, if we think about, maybe the situation where we have to do integration by parts multiple times, which I believe this is going to be one of those examples, and we'll see why in a minute. Each time you lower your power by 1, eventually you'll get to a constant. So let's think about this. If we then take the derivative of 2x, that's just going to be 2. We get to a constant. And that'll make more sense as we kind of work through this. But the point is, if you have a power function, you usually want to make it your u because you want to lower your power and get to a point where your function is going to be easier to deal with rather than more complicated to deal with. Because if we raise our power and get x cubed, if we do take it a step further and take the antiderivative of this term again a second time through the problem, we're going to end up with an x to the 4th term. And, if that keeps going, it's never going to reach an end. It's just going to kind of infinitely loop. And again, I'll explain a bit more of kind of what that means and why that's significant in a minute as we work through this. But for now, let's go ahead and just say that our u is going to be x squared. Our dv is going to be the cosine mx dx. So then, again, this next step of an integration by parts problem, once you have determined what your u and your dv are, you're just going to find du and v. You just find du by taking the derivative of u. So the derivative of x squared is 2x by the power rule. The antiderivative of cosine of mx dx. And you could, if you wanted to think about how to actually solve this, you could do this using U-Substitution. I'm not going to go into all that because it's going to work basically the same for, any constant times x in here. But if you want to, try that on your own, that would be a good exercise for you. But you could integrate this with U-substitution. If you do that, what you're going to find is the integral of cosine times some constant times x is going to be sine of mx times, let me move this, sorry. Just over a little bit, times 1 over m. And we can quickly kind of check this just by thinking about going the other direction. So instead of taking the antiderivative, if we took the derivative of this term here, this 1 over m times sine of mx, we would do this using the chain rule. And what you would find is the derivative of sine is cosine. And then by chain rule, we would have to multiply by the derivative of mx, which would be m. Multiplying by m would cancel with this 1 over m, getting us back to cosine of mx. So that's just kind of a quick check. And then we do also need our dx over here. Dx is always going to be with du and with dv. So now, once we have that, we can use our integration by parts formula. Again, this integration by parts formula is on my integral calculus cheat sheet. Link is down in the description or the pinned comment where you can check that out. But that formula just says if we have the integral of u times dv, which is what we started with, right? We had u here and dv here. The integral of u times dv can be rewritten as u times v minus the integral of v times du. Okay. Perfect. So now we can just apply this formula, which basically just means we're going to take our u, or I'm sorry, our u, our v, and our du and plug them into this formula. So we know that this integral we started with is going to be equivalent to u times v, so x squared times 1 over m sine of mx, which would be the same as 1 over m x squared sine of mx, minus the integral of v times du. So this whole thing here times 2x dx. So 1 over m times 2x sine of mx dx. Okay. So now here's the interesting thing about this problem. We still have an integral that's not super easy to deal with, right? We still have like an x times a sine of mx in here. That's not super easy to deal with. So it kind of seems like maybe this was a dead end. But this goes back to what I was kind of touching on previously of having to use integration by parts twice in one problem. It's not all that uncommon that you would have to do something like that. And it happens a lot when you have a power function times a trig function. And that goes back to what I was saying before. If we imagine taking the derivative of now this 2x term, that derivative is just going to be a constant. So basically the power each iteration through is going to keep on going down and down and down. So basically whether we had x squared times some trig function or x to the 100th power times some trig function, we could keep applying integration by parts, being sure to take the derivative of the x to the n power each time, and each time we'd get one iteration closer to an answer. Of course, that would be a long mess of a problem, but having just x squared is a little bit more manageable. But let's kind of simplify this a bit, and then I'll kind of show you what I mean. What we have out here outside the integral is not going to change at all. We're still just going to have 1 over m x squared times sine of mx minus, and then we can pull the 1 over m, because m is a constant. We can pull the constant out of our integral. And we can also pull this 2, which is a constant, out of our integral. So we're going to have 2 over m times the integral of x times sine of mx dx. Okay, so again, now we can do the exact same process this time. We can say, again, our u is going to be x, because we want to keep taking the derivative of that x or x squared term. And then our dv is going to be this sine of mx dx term. So one quick note, really, with any integration by parts problem where you have to apply integration by parts more than once, or applying integration by parts twice in one problem, whatever you make, whichever term you made your u the first time through, you typically want to pick the resulting term that corresponds with that one, your u, again the second time. And therefore, whatever was your dv the first time, the term kind of corresponding with that is going to be your dv the second time. So in this case, our trig function was our dv both times, and then the x, or the x squared term, was our u both times. And you would want to continue that pattern if you had to apply integration by parts more than twice in the same problem. This trig would want to continue on as dv, and this other term, which the power would continue lowering, like I keep saying, and that's because we would keep on taking the derivative of that term rather than switching to then taking the antiderivative, which would kind of just undo the previous step. So again, now we're going to do the exact same process we did for the first half of this problem. We're going to take the derivative of x, which is just 1, and then we have our dx here, and then we're going to take the antiderivative of our dv term, which pretty similar to what we did in the last time through. We're just going to get 1 over m, negative 1 over m, times cosine of mx. Because again, if we imagine taking the derivative of this, by chain rule, the derivative of negative cosine, actually, wait a minute. It's going to be positive cosine, I'm sorry. No, it is negative. My mistake. So the derivative of negative cosine, because negative cosine starts with a positive slope. So the derivative of negative cosine is positive sine. And then by chain rule, we have to multiply by the derivative of this inside term here. The derivative of mx is just m, which would cancel with 1 over m. So just kind of a quick check there. So then we can apply, again, this integration by parts formula. So we're going to get the integral of u times dv is just going to be equivalent to u times v, so x times negative 1 over m cosine mx. So negative 1 over m x cosine mx, u times v, minus the integral of v times du. So minus the integral of v times du. Well, 1 dx is just dx, basically. So minus the integral of negative 1 over m cosine mx dx. Okay. And then the rest of this is just going to carry on down. So we're just going to have all this stuff here that was outside the integral. Basically, this piece here is just equivalent to this integral that we had here. So the 2 over m is going to remain, being multiplied by all this stuff, because all this stuff is equivalent to the integral here. And then the rest is just going to remain exactly as it was. Okay. So now we can simplify this a bit further before we worry about this integral here. We're not done yet. We do still have an integral here, so we have to integrate still. But let's go ahead and simplify this a bit. So this term is not going to change, but we will want to distribute this negative 2 over m into the parentheses here, because inside here we have these two terms here. So let's do that. 1 over m x squared sine mx is going to stay out here. Minus 2 over m times negative 1 over m is plus 2 over m squared times x cosine mx. And then negative 2 over m times negative, and actually let's go ahead and pull this negative 1 over m out of our integral, because it is just a constant. We can just pull it out like that. So pulling that out, we're going to have a negative here, a negative here, and a negative here. 3 negatives times each other makes a negative, and that's just because we're distributing this whole term here into to the parentheses to this term here. So I know this is getting kind of messy, but negative, negative, negative makes a negative. 2 over m times 1 over m gives us 2 over m squared. And then let's see here. Okay. And then, so that's accounted for this 2 over m distributing in. We've also pulled this negative 1 over m out of our integral. So we still have the integral itself, and we're taking the integral of cosine mx dx. Okay, so now we still have to integrate this cosine mx dx. Well, now this is not any more complicated than the integrals we've already done. We've already integrated sine of mx dx, and before that, we actually already integrated cosine of mx dx. So now we have an integral which finally, after applying integration by parts twice, finally we have an integral that's actually simpler to evaluate than the one we started with. Well, we already found out that the integral of cosine mx dx is 1 over m sine mx. So basically, this whole thing here is just 1 over m sine mx. We already figured that out the first time applying integration by parts. So we can kind of just plug that in for what's in the box here, this integral. And then again, we still have this minus 2m squared being multiplied, or minus 2 over m squared being multiplied by that. So, 2 over m squared times 1 over m is just 2 over m cubed. So we'll go ahead and simplify that. Okay, and then the rest of this is just going to carry on down. There's not any, integrating to do with any of this. We've already done the integration part of all this. If there were some more simplifying to do, we definitely could do that, but fortunately, we took care of all that already on the last step. So this should be the fully simplified version of our solution. So this here now is the integral based on using integration by parts twice of this original function that we started with up here. All right, still not seeing any questions in the live chat. If you do have any questions, feel free to drop them. That's why I do these live instead of pre-recording them. All right, and I do have one more example for you guys here. I think should be a fun one, kind of an interesting one, and the problem actually kind of, makes it pretty clear what is interesting about it. This problem tells us we're going to first make a substitution and then use integration by parts to evaluate the integral. So in this problem, we're going to have to use integration by parts and U-Substitution. Okay, fortunately, both of these formulas are on my Calculus 2 study guide. Again, link is down in the description below and the pinned comment as well if you want to check that out. Available for instant download, so go grab yourself a copy of that. But both of these formulas are on there, so that should kind of help make things a little bit easier for us. But we're going to be using U-Substitution with integration by parts in this example. Fortunately, it does tell us to first make a substitution and then use integration by parts. So that at least helps eliminate one choice that we would have to make, which is which thing to do first. So we know we're going to have to make a substitution. So we'll start there first of all. When you're doing U-Substitution, first thing you need to figure out is what are you going to call your U? What's going to be the thing that you substitute? Well, typically when I'm thinking about that, I like to kind of think about what are your options? What are the different choices of what you can make U? You're never going to want to make U the entire thing. So we're definitely not going to say U equals t cubed times e to the negative t squared. It's not going to get us anywhere. You also, so we don't want to say t cubed e to the negative t squared. You don't want to do that. You also never want to say u equals t. U equals just whatever variable you're dealing with, because again, that's not going to get you anywhere. So we can right off the bat eliminate those two choices. Okay, so what choices do we have? Well, usually you just want to kind of think about piece by piece, basically what options are there. Well, we could call it just this piece, so just t cubed. And we're just brainstorming here, just throwing down options, so don't think too much about it, just kind of break down the different pieces. We could say that u is going to be this whole thing, e to the negative t squared. We could say that u is going to be just the negative t squared, just the power. Or maybe we could say that u is just going to be just t squared, just the positive version. I would say if you have a situation like this, negative t squared and positive t squared, usually that's not really going to make a difference because they just differ by a constant. When integrating, differing by a constant usually means there's no difference, but not always. I mean, certainly worth considering these two different options. But let's go ahead and kind of think about how this is going to go. And this is a very weird example because typically the advice that I give and that you would probably, hear in your textbook or from your teacher or professor, when you're trying to think about what to make your u, typically what you want to do is pick your u so that the derivative of that thing is somewhere else in your equation. Well, let's just kind of quickly think about what the derivative is of these four different options that we have here. First of all, the derivative of t cubed is 3t squared. The derivative of e to the negative t squared is going to require chain rule. I'm not going to go into all the steps of finding that, but just quickly, it would be e to the negative t squared times negative 2t. The derivative of negative t squared would be negative 2t, and the derivative of t squared would be positive 2t. So these are kind of our options. And you want to think about this because if the derivative of the thing that you're choosing for u is somewhere else in your equation, usually that's going to result in those things canceling out and creating a simpler problem for you. In this case, we can see that if we make our u be t cubed, the derivative is 3 times t squared. We do have a negative t squared right here. So right off the bat, that seems like a decent option. Of course, they differ by a constant. Again, that's fine. We have a negative 1 as our coefficient of this t squared here, and we have a positive 3 as our coefficient here. Again, differing by a constant usually is not really worth worrying about because what we care about is the t squareds canceling out. However, before we kind of go down this route, the fact that this negative t squared is in an exponent here is going to prevent it from canceling out the way we want it to. That's kind of a weird thing to say without showing you what that means. But, if you want to get a little better idea, go ahead and proceed. Go ahead and let's just, pretend for a sec that you're going to say u equals t cubed and go down the path of solving that with U-substitution. You would find that the t squared in this du term that we would introduce would not cancel with the t squared in this exponent here. So it wouldn't end up helping us because we would still have the t squared up in the power, and it wouldn't be able to simplify in a way that would allow us to integrate with respect to u. So although this does look like the best option right off the bat, it's actually not going to end up working, unfortunately. Okay, so let's go ahead and eliminate that option. Here, right off the bat, we can see if we made our u this whole thing, this whole term right here, we would introduce another e to the negative t squared, which is going to get in the way somewhere else. So again, that's probably not going to work very well, which really just leaves us with these two options. Okay, so between these two options, seems like they're not the greatest choices. Let me just clean this up here real quick. But obviously, they're the only two choices we have left. So we got to pick one of them. The question is which one? Well, usually if you have two options that are super similar like this and just differ by a constant, it's usually best to go with the one that includes the constant in it. So in this case, u equals negative t squared. Because again, when you get to the actual canceling out step and the integrating step, differing by a constant, you're still going to be able to pull that constant out. It's not really going to change the integration you have to go through. So it doesn't really make it really all that different, to be honest, but it will make things a little bit simpler for you if you just include it in there. So let's go ahead and proceed with that. And again, this seems weird. Seems like it's not really going to help us, but that's where the integration by parts portion is going to come into play, which is going to be interesting. So we're going to go with u equals negative t squared. So the first step of doing u substitution, once you have figured out your u, is to then figure out your du. Well, again, the derivative of du is just going to be the derivative of u. The derivative of negative t squared is negative 2t dt. We're going to put that in there as well. That's just kind of a little notational caveat of u substitution. Okay. So now what we would want to do is typically you would want to take this and solve it for dt. Well, we could do that just simply in this case by dividing both sides by negative 2t. And we get dt equals du over negative 2t. Okay, so now what we can do is go back to our original integral, which, let me just rewrite that down here. We had the integral of t cubed times e to the negative t squared dt. Okay, so now once we have figured out our u and our du, what we want to do is substitute, or I'm sorry, our u and our dt, we want to substitute this piece out of our equation for u. So we're going to replace this with a u, and that is a negative t squared there. And then we're going to replace our dt with the thing that we just solved for dt, so du over negative 2t. So if we do that, we're still going to have t cubed out here. We're going to have e to the u, and then we're going to have times du over negative 2t. Okay, so seems weird, right? This doesn't really seem like this got us any closer. Let's think kind of how this will simplify, though, because what you're going to find is this t cubed is going to cancel with, or I'm sorry, this t here is going to cancel with one of the t's here. So this is going to change to a 2, and this is going to cancel. So we're going to get the integral of t squared times e to the u du, and then we can pull out a negative 1/2 from the integral. So we'll just pull this negative 2, which is on the denominator down here, out of the integral completely. So now this seems, like I said, doesn't seem like it got us anywhere, because now we have e's and u's all stuck together. However, look at what our u was. It was negative t squared. Well, that's kind of interesting, because now here we have another t squared. Well, if u is negative t squared, we could figure out that t squared would just be negative u, right? If we just multiply both sides by negative 1, we get t squared equals negative u. Well, now what we can do, if we know t squared equals negative u, we can put negative u in for t squared right here. So that's just going to get us negative u times e to the u du with a negative 1/2 out front. And then again, we can pull our negative out from our integral, and it's going to cancel with our negative sign here. So actually, the only thing we have to integrate now is we just have 1/2 times the integral of u times e to the u, which definitely looks a lot simpler than the integral we started with of t cubed times e to the negative t squared. Sorry about that if you can hear barking. So now what we can do, like the problem suggested, now that we've done the u substitution, is we can apply integration by parts. So this is going to end up working out very similarly to the second half of the last two problems I did. But basically, and this is just kind of a notational problem, what I'm actually going to do because our integration by parts formula uses u and dv, I'm going to change these to x's. So instead of integrating u times e to the u, we'll integrate x times e to the x. I think I've actually made another video on how to do this exact integration. And changing the variable like this, it does not change the problem at all. It's the exact same thing. All we've done is replace our u with x exactly. And that's why I say when you're doing U-substitution, never say u equals x or u equals t. It doesn't get you anywhere because it results in the exact same problem, the exact same integral. So now what we can do is we can apply our integration by parts formula, which just means we need to find our u, find our dv. We would then find our du and our v, and then use the formula. I'll just jot the formula over here. The formula is the integral of u times dv equals u times v minus the integral of v times du. Okay, so again, our u is going to be the thing that's better to take the derivative of. Our dv is the thing that's better to take the integral of. Looking at our two options here, x and e to the x, e to the x is not going to be better or worse because e to the x is a function where the derivative and the integral is exactly the same. Kind of similar to the trig functions where they're the same but differing by a constant, except e to the x is actually exactly the same. If we take the derivative of e to the x, it's e to the x. If we take the antiderivative of e to the x, it's still just e to the x. So this one makes no difference at all. However, x is usually going to be better to take the derivative of than the antiderivative, because the derivative of x, if we say u equals x, our du is just going to be 1 dx, which 1 is a pretty great thing to kind of introduce in there. So we'll make our e to the x dx be our dv. The integral of e to the x is just e to the x. So now that we've figured out these four pieces, we can apply the formula here. So we're going to get u times v, so x times e to the x, minus the integral of v times du, so minus e to the x times 1 dx, which is just e to the x dx. And then again, we still have this 1/2 out here. And all this stuff here, this is very important to make sure that you put parentheses around this, because what this formula tells us is that this integral here is equivalent to u times v minus the integral of v times du, which is what we have inside the brackets here. So whatever constant you have out here needs to distribute to both of these things. That is very important. If you don't put those parentheses around there, you're going to end up with the wrong answer. So what we can go ahead and do now is distribute our 1/2 into there. So that would be 1/2 x e to the x minus 1/2 times the integral of e to the x dx. The integral of e to the x dx is just e to the x. So this, oh wait, nope, sorry. Hold on a second. I don't think we're quite done yet here. Let me double check. Yes, we are not done yet. There's one more thing we need to do. Because remember, we did a substitution, which we have not undone yet. So the last kind of step of U-substitution is to then undo your substitution, right? We decided that u equals negative t squared, but now we need to kind of undo that. And this is kind of a weird situation because right here, I switched from u to x. I just decided that x and u were the same because of this weird notational thing with, the fact that the integration by parts formula uses x, or uses u, I'm sorry. So basically right here, I kind of made the decision artificially that u equals x, and I just changed the variable there. So we need to go back up here to our substitution of u equals negative t squared. Well, u equals x, so therefore x equals negative t squared. So we need to take that all the way down to here, keeping in mind that x equals negative t squared, and substitute that back in. So what we basically have to do is go to all of our x's and replace them with negative t squared. So actually our final answer is going to end up being 1/2 negative 1/2, because it's negative t squared, times t squared times e to the t squared minus 1/2 e to the negative t squared, which we could kind of factor out an e to the, sorry, this should be e to the negative t squared here. So we could factor out a negative 1/2 e to the negative t squared out of this. So negative 1/2 e to the negative t squared times, if we take negative 1/2 e to the negative t squared out of here, we're just going to have a t squared there. If we take it out of here, including the negative sign that we pulled out, we're going to have plus 1. So this would be our final integral and our final answer. And I should make sure I'm not blocking that. Okay, cool. Yeah, sweet. So that's it. Not seeing any questions in the live chat. If you do have one, feel free to drop it in there real quick. We'll see if we can get your question answered, even if it's not on topic, before we wrap things up here. But otherwise, all right, cool. Yeah, not seeing any questions. If you haven't already, if you got some value out of this video, please go ahead and hit that like button down below. It's a huge help to the channel, so we can keep making more videos like this and get these out to as many people and keep growing the Jake's Math Lessons community. And if you haven't already checked it out, all the stuff we just went over is discussed on my Calculus 2 study guide or my integral calculus cheat sheet. There's a link down below in the pinned comment and the video description as well, so go check those out. Should be back on schedule, back to our Monday night live streams next week. So hope to see you there. Thanks, and see you then. See you next time.